Module 2019, Unit 6. The first question, a student investigated how the time period of a simple pendulum vary with the length. Like when we change the time period, how the length changes using the apparatus shown. As we change the length, how the time period changes. Retort strand is there, a spring and a pendulum. The pendulum perform a simple harmonic motion, hence its time is given by the equation t is equals to 2 pi under root L over G. State a reason for using a small displacement. Like student displaces a pendulum and record the time for 10 oscillations. And why the amplitude should be small? Because the condition is that when a simple harmonic motion is there, for a large amplitude, like if the derivation, this formula is only derived when theta is very small. If the theta is very large, then this statement, this equation won't be accurate. So main reason for keeping a displacement, the main reason why we keep the displacement very small or a short distance is there, so that like angle should be small, or we can also ensure that the amplitude does not affect the time period. So main reason is to keep the angle small, because this formula is only derived for a small angle. And when we keep the angle small, as a result, the amplitude does not affect the time period. Then the student use a pin as a timing marker. Explain how placing a pin at the center of oscillation will lead to more accurate value for 10 oscillations, like total time for 10 oscillations. So if we keep this pin here, like this pin is used as a marker, like because as this pendulum is vibrating, completing simple harmonic motion, oscillating. So this pin is used as a reference. So using this pin, what we can identify, like there's only fixed point in the oscillation, so where we can velocity at this point will be maximum. So as a result, what will happen, the uncertainty in the time, we can reduce the uncertainty in the time. That is one reason. Or like there's only one fixed point in the oscillation, so the amplitude may vary because of a damping. So using that, because the question is why the pin is placed, the student use a pin as a timing marker. Explain how placing a pin at the center of oscillation leads to more accurate. Because why at the center? Why not at the edges? Like example, say a pendulum is performing, like a pendulum is there oscillating. Why we did not place a marker at the extreme position? Why we place a marker at the mean position, the center position? So what is the reason for that? The main reason, you can mention, like because when it is oscillating, if the marker is placed at the extreme position, so what might happen, the amplitude might vary. Like when it is oscillating, it won't reach the marker again, so it won't be accurate. Like how we cannot recover, as it is vibrating, the amplitude of the vibration will reduce, so we cannot recognize whether it crossed that point or no, or because it won't reach that point, so we cannot account how many vibrations are there accurately. That's why the when a marker is placed at the center, because every time it will cross the center, so we can easily recognize. So answer for this one, why the marker is placed at the center, not at the other point, because if marker was placed at the extreme position, so due to a damping, the amplitude may vary. So this is the only fixed point in oscillation, like keeping a point as fixed, and we measure the time period with reference to this point. Is it clear, this part? Then the student obtain the following results. So these are the results. We need the average time for 10 oscillation, and then we need the time for one oscillation. So there are 1, 2, 3, 4, 5 values are there. If you want to take an average, we will sum and divide it by the total. So we have 10.15, we have 10.32, we have 10.20, we have 10.28, we have 10.24. So this will be 10.238, which will be equal to 10.24. So when we add and divide, and then we need a time for one oscillation, so we divide by 10, so it will be 1.02. And calculate the percentage uncertainty. How to calculate the percentage uncertainty for a group data? That is the maximum minus minimum divided by 2. And then that, like, first we get the uncertainty, then we get the how to calculate the uncertainty in the measurement. The uncertainty in the measurement is, for a group data, it is maximum minus minimum divided by 2. And to get the percentage uncertainty, maximum minus minimum divided by 2 and then divided by mean. And the percentage uncertainty, because we want for time t we are measuring, so the percentage uncertainty, we want the percentage uncertainty. Percentage uncertainty is uncertainty divided by the value recorded into 100. How to work out the uncertainty of a group data? Whenever we have a data, so it is maximum value minus minimum divided by 2. The maximum value of this is 10.32 and the minimum value is 10.15, and that is divided by 2. So 10.32 minus 10.15, and that is divided by 2, which is 0.085. So 0.085, that is the uncertainty in the measurement. And then the percentage uncertainty is an uncertainty which is 0.085 divided by value which we record. What value we record? We record 10.24. Sorry, the average which we record, that is 10 point, mean is there. For a group data, uncertainty divided by value recorded, or you can also say mean, because it's a group data. So group data we divide by mean into 100. So it will be 10.24 and into 100. So the final answer for the percentage uncertainty, it will be 0.085 times 100 divided by 10.24. So it is 0.83%. So 0.83% is the uncertainty in the calculation of time. Is it clear how we work out the uncertainty for a group data? The next one, the student doubled the length of a pendulum. She made the following prediction. If the time period is, if time period for short pendulum is Ts, the time period for double length is Td, then Td square and Ts square should be equal to 2. Justify this prediction. So you have to use the first relation here. Like we have the formula T is equals to 2 pi under root L over G. So if I square this equation, so it will be T square is equals to 4 pi square L by G. If we say the pendulum of the like a shorter length is Ts, and for double length like Td square will be equal to 4 pi square. This will be 2L divided by G. Or I can say, if I simplify this equation, I can say Ts square over L is equals to 4 pi square by G. And if I move 2L this side, like in to Td square is equals to 4 pi square by G. So on the right hand side, we have two equations are same. Right hand side are same. So we'll compare the two equations. So we can say one side we'll have TD square over 2L, and the other side will have TS square over L. Then we simplify this. L will cancel with L. TS square will go there in denominator. So it will be TD square over TS square is equals to 2. Means when we take the square ratio of their squares, we'll get 2. That is right. We are getting 2 as a answer. So we use the first equation. We just substitute the values. Like the first one, the time period for a short pendulum is TS and time period for the double pendulum is TD. So TD over TS square is equals to 2. The student determined time for a long pendulum, and that is 1.461 plus minus 0.011 seconds. So that is the value recorded, and this one is the uncertainty. Determine whether her results support her prediction. So what we have to do, like we have this is a time period. This is a time period for a shorter pendulum. And with the percentage uncertainty, we always have the percentage, which is 0.83, the mean time period for a shorter pendulum. And then this is a time period for a longer pendulum, which is 1.461, and with the uncertainty of 0.011 seconds. So what we will do, we will find the value for this TD square over TS square, and we will calculate the total uncertainty, like the percentage, and we'll compare the percentage uncertainty with percentage difference. The idea is that, like, see, we are finding TD square over TS square. This is a 4-mark question. And usually in unit 6, you will find the uncertainty, very common topic. So TD square over TS square, what we'll do, we'll find two things. We'll find percentage uncertainty and we'll find percentage difference between the two values. And then we will compare the two values. Like if the percentage difference is less than the percentage uncertainty, like if that is the case, if the percentage difference between the two values is less than the percentage uncertainty, it means two values are same. Like it support that TD over TS square should be equal, TD square over TS square should be equal to 2. But if the percentage uncertainty is higher than the percentage difference, then it does not support, like the two values are not equal. So how to do such? First, we will find the value for the TD square over TS square according to the values which we calculated. Then we'll find the percentage uncertainty, and then we'll find percentage difference. Percentage differences can be calculated like sometime. First, we'll do this one. So we have TD square over TS square. So TD, this one is 1.461 square divided by TS square. The time period for the shorter one was 1.024 square. And when we divide, we get 2.04. That is the ratio between TD square over TS square. Now we'll find percentage uncertainty. Look, whenever quantities are divided, multiplied, first you'll find the percentage uncertainty and then add the total percentage uncertainty. So what was the percentage uncertainty in TS? That was 0.83%. We'll find the percentage uncertainty in TD. How to find the percentage uncertainty in TD? That is the uncertainty, which is 0.011 divided by value recorded 1.461 into 100. This will give us the percentage uncertainty in TD. So it will be 0.011 times 100 divided by 1.461, which is 0.75. So 0.75% is the percentage uncertainty. Now, what is the percentage uncertainty in the calculation of TD square over TH square? So how TD, what is like total percentage uncertainty? in a calculation of TD square over TS square. First, because there is a power 2, so the percentage uncertainty will be multiplied by 2. So TD is having uncertainty of 0.75 and then times 2. Why times 2? Because the power 2 is there. And plus, what is the uncertainty in TS? That is 0.83. And because it is a square, so that will also multiplied by 2. So what is the total percentage uncertainty? This will be 2 into 0.75 plus 2 into 0.83. So that will be 3.2. So we calculated the percentage uncertainty, which is 3.2%. Is it clear? The percentage uncertainty in the value for TD square over TS square. So when quantities are divided or multiplied, we add the percentage uncertainties. And because the power 2 is there on each of them, so the percentage uncertainty will be twice. If there was a power 3, then the percentage uncertainty will be twice. Is it clear this part? How I work out the percentage uncertainty? Then how to calculate the percentage difference? The percentage difference is a maximum minus minimum divided by mean, or uh, if you have the standard value, because according to theory that when TD square over TS square, we should get 2. So the formula is like we want to compare this with 2.04. So maximum 2.04 minus minimum divided by standard. Because we should get 2, we are finding how much difference is there from the standard. So when we simplify this, this will be about 2%. So when you compare this, you can see the percentage difference when we calculate is less than the percentage uncertainty. It means, so measurements support the prediction like the values are equal. Like this value is equal to this one. Is it clear? So it support the prediction like as the percentage difference is less than the percentage uncertainty. If it was other way around, the percentage difference is more, then it does not support. So just remember, if it is less, it support, it's equal. If it is more percentage difference, then the uncertainty, then it does not support the theory. And AC alternating current in the primary coil generate a magnetic field. This induce an EMF across the secondary coil. Explain how EMF is induced across the secondary coil. So you have to explain here electromagnetic induction, that alternating current produce variable magnetic field, and the change in a magnetic flux linkage induce EMF. So AC input produce variable magnetic field which induce EMF in the secondary, or changes the magnetic flux linkage which induce EMF. Student has the apparatus has shown the diameter D is there and the two coil, and the EMF induced across the secondary coil. The EMF induced in the secondary coil is given by this formula where K is a constant, N is the number of turns, I is the current, D is the distance, as shown. A student investigate how V vary with D. So student investigating how V vary with D, variation in V and D. Write a plan to determine the K. Graphical method. So means you have to plot a graph. So student is varying V and D. So when we compare with the equation of straight line, y is equals to mx plus c, there is no y-intercept. So if on y-axis, if we plot v, on x-axis, we plot 1 over d cube. Because we want d, we are varying d and v are changing. So what will be the gradient of this will be a straight line passing through origin, and the gradient of this line will be equal to kn. Kn and I. And after knowing Kn and I, the gradient, so gradient divided gradient divided by Ni, the number of turns in the current, we can find the value for K. as we compare with the equation of straight line. So the first part, that is the overview. The first part, a circuit diagram to show how primary coil is connected with any additional component required. So this primary coil, because what we should have, we want to measure the current. So there will be an ammeter, and so there should be an ammeter, the switch should be there. Then a variable supply, you can have a variable supply, so you can change the voltage. Or you can have a variable resistor. Instead of that, you can also have a variable resistor. The next part, measurement to be made with additional apparatus required. So what measurements we should, because we are varying d, the distance, and uh, where v is the voltage induced. So what we need a meter rule or a meter scale to measure the distance between the two coils. And we here in the secondary, we need a voltmeter to measure the voltage produced. So we have to measure the voltage produced. So we need a voltmeter for that. And the distance is there. How we measure the distance? By using a meter rule or a meter scale. The graph to be plotted and how it would be used to determine K. As we did already, that how we can work out the value of the K. Because we'll plot a graph. As I mentioned, we'll plot a graph between V on y-axis and 1 over d cube on x-axis. So gradient will be equal to K and I. So if I need K, gradient divided by Ni is equals to K. Then uh, then a statement of a significant source of uncertainty. What might be source of uncertainty? First thing, these alignment, like, because this is not a solid surface, so it will be difficult to align these coils, primary and the secondary coil, in line. That is will be the one major source of uncertainty. And another, when we are measuring a distance here and we plot a graph for 1 over d cube, so percentage uncertainty will be 3 times. Like as we measure the distance and then we plot a graph for v and 1 over d cube. So what will the uncertainty, percentage uncertainty will be 3 times, because there is power 3. So uncertainty will be 3 times. So there will be higher percentage uncertainty in measurement of a d, in the value of a d, and d cube, 1 over d cube. So this was the experiment. You have to write answer according to the question. The surface temperature of a star can be estimated by determining the maximum wavelength at which the peak power emission occur by the star. As a student astronomer observed the red giant, he measured the radiation flux, and the data was plotted as shown for different wavelength emitted out and the radiation flux. Draw a line of a best fit to show radiation flux. Draw a line of a best fit to show where the radiation flux is maximum. So for such, how we can work out the maximum radiation flux? Look, you don't have to draw the straight lines here, because when you try to draw a straight line, all the points will, you cannot have a best fit straight line here. And the points are not too many points are there, so it will have a higher percentage uncertainty. So we'll draw like a smooth curve. If the points were straight, like if all the points were lying on the pattern or making a straight line for increasing and decreasing, that time we will draw the two straight lines. Like we'll draw one straight line for this pattern, another one for the other. and that will give us a maximum. But not in this case, as it shows a pattern. It is like a curve, a smooth curve. So you can draw like this. It will be approximately 820 to 35, I think. So in this region, we might have a maximum value. The next one, estimation is there, that how to estimate after drawing the maximum value, just where it intersects. So which position we have on x-axis, that will be the lambda max, the maximum wavelength. It's not a maximum wavelength, it's a wavelength at which the flux is maximum. Then calculate the T. How to calculate T? There is a formula which relate the wavelength, and that is in unit 5 about the Wien's law about the stars, that state that lambda max into T, like when T is multiplied with lambda max, that is equals to 2.898 into 10 to the power minus 3. That's a formula. So if I need T, we'll divide by lambda max, we'll get the value for T. So just two reasons why the value of a lambda max might not be accurate. First thing, from your graph, you can identify there is no repetition. Like student did not repeat his experiment or her experiment. It's the same, like only with the 1 point, like having a certain points he took the wavelengths, but it's not, repetition is not done for this experiment, and not enough reading. Whenever we have like variation is there in the values, so we should have more readings in this region. Before that, no problem, but we should have more readings in this region so we can have more prominent shape. Like we can identify what is the accurate value for a lambda max in which the radiation flux is maximum. And this is having a higher uncertainty because the variation is there. We cannot draw a straight line. If it was a curve, then curve is having a higher uncertainty as compared to a straight line. The next question, a student investigate the absorption of a gamma radiation by a lead using the apparatus, the GM tube, rate meter. She recorded and corrected the background. Why is possible to correct the, explain why it is possible to correct the background count rate. Because usually background counts are more or less constant, and background counts are leads to systematic error, like it is there in the system. Systematic error can be corrected, but random error cannot be. Like if you're doing any experiment, if there is a change in temperature, change in pressure, that might affect your result, but you cannot do any correction for that. But systematic error is there, like zero error is there. So you can, if it's a positive or negative zero error, you can rectify the zero systematic error. So she recorded and corrected why it is possible to correct the why it is possible to correct for background radiation, because the background radiations are usually constant, more or less, not changing, and this background radiation is a systematic error. Systematic error can be rectified, but random error cannot be rectified. Like you can do correction for systematic error, but not for random error. Then student record the corrected count rate for different thicknesses. The relation between C and the total thickness is there. C naught is a count without any lead sheet and mu is a constant. Why plotting a graph for L and C will produce a straight. So first what we do, we'll take L both sides. When I take L both sides, so this will be L and C is equals to L on C naught e raised to power minus mu x. What is the relation for whenever in Ln two quantities are multiplied, we write them separate. Ln A plus Ln B. So this will be Ln C is equals to Ln C naught plus Ln e raised to power minus mu x. And remember, Ln and E functions are anti-functions. So they, like if there is a Ln e raised to power x, this will become x. Ln E will cancel out. So here Ln and E, they will cancel out. So it will be Ln C is equals to Ln C naught minus mu x. Because mu x is a power of E, that's why it will be there in as a number. If I rearrange this equation, because we are plotting a graph between Ln C and x, so if I rearrange, I will say Ln C is equals to minus mu x plus Ln C naught. Now I compare with the equation of straight line y is equals to mx plus c. And we are comparing ln c with minus mu x plus ln c naught. So if on y-axis we have ln c, on y-axis we have ln c, on x-axis we have x. So what will be the gradient? The gradient will be minus mu, and mu is a constant. So minus mu will also be. So the gradient of this graph will be equal to minus mu, as mu is constant, so it will be a straight line. But this straight line does not start from origin. Why? Because there is a y-intercept, ln c naught. So this will be a straight line but above origin, where the positive y-intercept represent the value for ln c naught. Is it clear, this part? So such equation you should modify in terms of log function. The student obtained the value for x and c. Plot a graph between ln c and x. Use the additional column. So here you will find ln c. Because this is c, so this will be ln c. Just substitute, like take ln 132, then ln 112, ln 95. And then plot a graph between ln c and x. And the shape of the, determine the mu. How to determine the mu? You have to work out the gradient. Like this grid is there. ln c should be on ln c should be on y-axis and x should be on x-axis. And when you plot a graph, it will be a graph like this, like the values. And work out the gradient, y2 minus y1 over x2 minus x1. The gradient of this line, which is y2 minus y1 over x2 minus x1, the gradient of this line will be equal to minus mu. So you just compare the gradient with minus mu. That will be the value for mu. So plotting of graph you have to do. This was June 2019 paper, Unit 6.